Look up at the night sky, past the shimmering stars and glowing galaxies, and tell me, what do you really see? On the surface, it might seem like a vast, beautiful emptiness, dotted with distant lights. But what if I told you that everything out there, from the tiniest dust particle to the grandest supercluster, is being shaped by forces we can't even see? The universe isn't just what meets the eye. It's an intricate dance of hidden powers, invisible hands pulling strings behind the curtain of reality itself. Think about that for a second. The very fabric of space and time, the motions of celestial bodies, even the fate of entire galaxies, all of it governed by mysteries we're only beginning to unravel. Take gravity, for example. We feel its pull every day, but what is it really? We can't see it, can't touch it, yet it dictates the orbits of planets and bends light itself. And gravity is just the beginning. There are forces at work out there so strange, so baffling, they defy our everyday understanding of physics. Dark energy pushing the universe apart at an ever-increasing speed. Quantum fluctuations sparking particles into existence from pure nothingness. Cosmic strings, hypothetical defects in space-time stretching across the universe like invisible scars from its birth. These aren't science fiction. These are real, tangible mysteries haunting the edges of our knowledge, shaping everything around us in ways we're still struggling to comprehend. That's why today we're setting off on a journey into the unseen. Together, we'll uncover 30 of the most mind-bending forces and phenomena hiding in the shadows of the cosmos. Some will sound like pure magic. Others might leave you questioning everything you thought you knew about reality. But one thing's for certain, by the time we're done, you'll never look at the night sky the same way again. Because the universe isn't just what's visible. It's the whispers in the dark, the hidden architects of existence, and the untold stories written in the spaces between the stars. So ready to lift the veil, let's begin. Ever reach out in the dark, certain something's there even though you can't see it? That's exactly how scientists first stumbled upon dark matter. The story begins with galaxies spinning so fast they should have torn themselves apart long ago. The stars on the outer edges whip around at speeds that defy logic, like a merry-go-round spinning so violently the kids clinging to the edges would go flying off. But they don't. Something invisible, something with immense gravitational pull, holds them in place. That something, we call it dark matter. Through painstaking observations, astronomers mapped these bizarre rotation curves, revealing galaxies were enveloped in massive halos of unseen mass. Picture dipping a spoon into honey, the way it clings in thick tendrils around the utensil. That's how dark matter clings to galaxies, its gravity shaping their very structure. But here's the twist. This mysterious substance doesn't reflect, absorb, or emit light. It doesn't interact with electromagnetic forces at all. We only know it's there because it tugs on everything around it, bending space-time like an unseen hand pressing down on a mattress. The hunt to identify dark matter particles has become one of science's greatest detective stories. Underground labs shielded from cosmic rays search for hypothetical weakly interacting massive particles that might occasionally bump into ordinary atoms. Others chase axions, ghostly particles so lightweight they could stream through lead like it's not even there. Meanwhile, supercomputers simulate the cosmic web, revealing how dark matter's gravitational scaffolding guided the formation of galaxies after the Big Bang. Those glowing clusters and filaments we see in telescope images, they're just the streetlights along dark matter's hidden highways, and yet, after decades of searching, dark matter remains frustratingly elusive. It makes up roughly 85% of all matter in the universe, yet we've never directly detected a single particle of it. Some theorists even propose we've been looking at gravity all wrong, that instead of invisible matter, we might need new laws of physics to explain these cosmic discrepancies. Whatever the truth turns out to be, one thing's clear: dark matter isn't just some minor cosmic curiosity. It's the unseen architect of our universe, quietly weaving the tapestry of reality while remaining forever just beyond our grasp. If dark matter is the universe's invisible scaffolding, dark energy is its mysterious engine constantly revving, pushing everything apart at an ever-increasing speed. The discovery of this force shattered one of astronomy's oldest assumptions, that the universe's expansion should be slowing down. Imagine tossing a ball into the air, expecting it to eventually fall back, only to watch it shoot upward faster and faster, defying gravity. That's precisely what astronomers observed in the late 1990s when studying distant supernovae. These dying stars, billions of light years away, were fainter than expected, meaning space itself had stretched more than predicted during their light's journey to us. The revelation came from two rival teams painstakingly mapping the cosmos using Type 1, a supernova stellar explosion so consistent, they're called standard candles. Like mile markers on a highway, their brightness reveals cosmic distances. When both groups independently found these markers dimmer than Hubble's law predicted, the implications were staggering. Not only was the universe expanding, but some repulsive force was overpowering gravity's pull. Einstein had actually foreseen such a possibility decades earlier with his cosmological constant, a mathematical fudge factor he later called his greatest blunder when Edwin Hubble proved the universe wasn't static. Now, ironically, that discarded idea might hold the key to our accelerating cosmos. Visualizing dark energy's effect is like watching time-lapse footage of a rising loaf of raisin bread. As the dough expands, every raisin moves away from every other raisin, but with dark energy, the oven keeps getting hotter. The raisins flee faster over time, and those farthest apart accelerate most dramatically. Supercomputer simulations show this relentless push, creating a future big freeze, where galaxies beyond our local group vanish over the cosmic horizon, their light never reaching us again. Yet for all its dramatic consequences, dark energy remains profoundly enigmatic. Is it vacuum energy, quantum particles flickering in and out of existence, exerting negative pressure? Or something entirely new, like a fifth fundamental force? The mystery deepens when we examine the cosmological constant problem. Quantum theory predicts vacuum energy should be a staggering 120 orders of magnitude stronger than what we observe. This discrepancy between prediction and reality is like calculating that a light breeze should have the force of 1 billion hurricanes. Some theorists propose dynamic explanations, quintessence fields that change over time, while others suggest revamping gravity itself once more. What's certain is that dark energy dominates the universe's energy budget, making up 68% of everything that exists. It's the ultimate puppet master, invisibly controlling the fate of the cosmos while remaining utterly inscrutable to our best instruments. As telescopes peer deeper into the cosmic web, measuring baryon acoustic oscillations, frozen ripples from the early universe, they're refining dark energy's fingerprint. Future missions like the Nancy Grace Roman Space Telescope aim to chart its influence across 10 billion years of cosmic history. Will it weaken, strengthen, or reveal itself as an illusion masking our incomplete understanding? However this cosmic thriller unfolds, one truth remains: dark energy isn't just another entry in physics textbooks. It's rewriting the final chapters of our universe's story, one accelerating galaxy at a time. Picture the quietest place in the universe, not the depths of interstellar space, but the vacuum right in front of you. What seems like perfect emptiness is actually a tempest. Quantum physics reveals that so-called empty space isn't empty at all. It's a seething ocean of virtual particles, flickering in and out of existence so fast we can't detect them directly. These quantum fluctuations aren't just theoretical quirks, they're real enough to push objects together in laboratory experiments. Take the Casimir effect, a phenomenon so bizarre it seems plucked from science fiction. Place two uncharged metal plates incredibly close together in a vacuum, and they'll snap toward each other as if pulled by invisible strings. Why? Because the space between them becomes too narrow for certain virtual particles to form, while outside the plates, particle pairs continue popping into existence unabated. The result, an imbalance of pressure that drives the plates together with measurable force. It's like standing in a crowd where everyone's constantly bumping into you from all sides until suddenly, two walls close in, shielding you from some of those bumps. The push from outside becomes stronger than the push between the walls, and they collapse inward. This isn't just a parlor trick. The Casimir effect proves that the vacuum of space crackles with hidden energy. Scientists call this zero-point energy the lowest possible energy a quantum system can have, which bizarrely isn't zero at all. Even at absolute zero, when all classical motion stops, quantum fields still vibrate with this residual energy. The implications are staggering. Some calculations suggest the energy in a coffee cup's worth of pure vacuum could boil all Earth's oceans. Of course, tapping into this energy isn't simple. These fluctuations exist on unimaginably short timescales, and extracting usable energy from them remains speculative. But that hasn't stopped bold ideas from emerging, like the concept of quantum vacuum propulsion. Imagine spacecraft that don't carry fuel but instead manipulate the fabric of spacetime itself, riding quantum fluctuations like surfers catching waves. NASA Eagleworks Lab has explored prototypes of such warp drives, though they remain firmly in theoretical territory for now. The quantum vacuum's restless energy might even solve another cosmic mystery, dark energy itself. Some theories propose that what we call dark energy could arise from zero-point energy permeating the universe, driving its accelerating expansion. But there's a problem when physicists calculate the expected energy density of the quantum vacuum. The result is impossibly large, clashing with observations. This discrepancy, known as the cosmological constant problem, remains one of the biggest unsolved puzzles in physics. Whether zero-point energy can be harnessed or fully understood, one thing's certain: the universe's empty spaces are far from tranquil. They're alive with invisible forces, whispering secrets about reality's deepest workings if only we can learn to listen. Think of the universe's first moments not as a slow awakening, but as an explosive sprint, one where space itself stretched faster than light. This is cosmic inflation, the theory that our infant universe underwent a mind-bending growth spurt, expanding exponentially in a fraction of a second. To grasp how radical this idea is, picture blowing up a balloon to the size of our solar system in less time than it takes to blink. Now imagine that balloon keeps expanding until it's larger than the observable universe. That's inflation's staggering scale. The concept emerged to solve cosmic puzzles the Big Bang theory couldn't explain. Why is the universe so uniform, with nearly identical temperatures in opposite directions? How did galaxies form if matter was originally too smoothly distributed? Inflation answers these by proposing that space expanded so rapidly, it stretched quantum fluctuations into cosmic seeds. Those microscopic wrinkles became the gravitational blueprints for future galaxies. Like zooming in on a smooth-looking painting to reveal hidden brushstrokes, our universe's large-scale structure might trace back to quantum fuzziness magnified by inflation's incredible stretch. Scientists hunt for inflation's smoking gun in the cosmic microwave background, the afterglow of the Big Bang. Teams like the BICEP collaboration scour this ancient light for B-mode polarization, a telltale swirl pattern that would reveal primordial gravitational waves rippling through spacetime during inflation. Finding it would be like uncovering dinosaur footprints frozen in mud, direct evidence of a violent transformational epoch, but the search is fraught with challenges. Dust in our galaxy mimics the signal, and false hopes like BICEP 2014 announcement, later retracted, show how painstaking this detective work is. Inflation's implications are dizzying. If space expanded faster than light, does that violate relativity? Surprisingly, no, because it's space-time itself stretching, not objects moving through it. Worse yet, inflation suggests our universe might be one bubble in an endless multiverse foam, where other bubbles host entirely different physics. Like a cosmic version of the Mandela effect, we may never see beyond our bubble's horizon, forever wondering what else is out there. The theory isn't without critics. Some propose alternative, bounce scenarios where a previous universe collapsed before rebounding as ours. Others argue inflation explains too much flexible enough to accommodate nearly any observation, making it hard to disprove. Yet for all the debates, inflation remains cosmology's leading origin story because it predicts cosmic features we've actually observed, like the universe's flat geometry. Whether it will hold up under future scrutiny or give way to something stranger, inflation reminds us that reality's first chapter was far wilder than we ever imagined. What if some of the universe's darkest secrets were hiding in black holes smaller than an atom? Primordial black holes aren't your average cosmic vacuum cleaners lurking at galaxy centers. These elusive objects, theorized to have formed in the chaos of the early universe, could be tiny time capsules from the first fractions of a second after the Big Bang. Unlike stellar black holes born from collapsing stars, these ancient relics might weigh anywhere from a paperclip to a mountain, all packed into spaces smaller than a proton. The idea first took shape when Stephen Hawking and Bernard Carr explored how density fluctuations in the newborn universe could have created micro-black holes. Picture the cosmos in its infancy, a seething, ultra-dense plasma where quantum effects ruled. In certain regions where matter got squeezed tightly enough, space-time might have pinched off into self-contained knots of gravity. No star death required just pure cosmological pressure cooking matter into microscopic singularities. Some could have evaporated instantly via Hawking radiation, while others might still be drifting through space today, invisible yet massive enough to bend light around them like cosmic magnifying glasses. Detecting these ghostly remnants pushes our technology to the limit. Atom-sized black holes would zip through matter like bullets through fog, barely interacting. Yet their gravity could leave telltale signatures, perhaps sudden flares as they evaporate, or precise distortions in starlight as they pass between us and distant stars. The Subaru telescope's Hyper-Subprime Cam survey has scanned millions of stars for such flickers, while gravitational wave detectors listen for the high-pitched chirps of tiny black holes colliding. Here's where it gets revolutionary. Primordial black holes could account for part or even all of dark matter. While WIMP and axions dominate the dark matter conversation, these ancient gravity wells offer an elegant alternative. A swarm of asteroid mass black holes distributed throughout galactic halos would gravitationally behave exactly like the unseen dark matter we've been tracking. NASA Roman Space Telescope may soon test this by searching for gravitational microlensing events that would betray their presence, but the theories get wilder. Some physicists speculate that certain primordial black holes might have survived to become Planck stars, exotic objects where quantum gravity effects prevent total collapse. Others ponder whether they could be seeds for supermassive black holes growing over billions of years. There's even a fringe idea that these microscopic singularities might occasionally collide with neutron stars, triggering cataclysmic gamma-ray bursts visible across the cosmos. Whether they're out there or not, primordial black holes force us to rethink fundamental assumptions. Their possible existence reminds us that the early universe was a laboratory for extreme physics, where conditions existed that we'll never recreate on Earth. And if we ever do capture definitive evidence of these cosmic fossils, it wouldn't just solve the dark matter mystery, it would rewrite the story of how our universe built its invisible architecture. Magnets fascinate us with their dual nature, always coming with both a north and south pole. Cut one in half and you don't isolate the poles, you just get two smaller magnets, each with their own pair. But what if nature broke its own rules? Enter magnetic monopoles, hypothetical particles carrying just a single magnetic charge, either north or south, existing completely independent of their counterparts. The idea first gained serious traction when physicist Paul Dirac tackled a tantalizing question in 1931. Why is electric charge always quantized in nature? His math revealed something startling. If even a single magnetic monopole existed somewhere in the universe, it would force electric charge to come in discrete, quantized amounts, exactly as observed. It was as though the universe had left a fingerprint hinting at these elusive particles, but Dirac's prediction wasn't just elegant math, it suggested a profound symmetry. Just as electrons carry isolated electric charge, monopoles would complete the picture with isolated magnetic charge, balancing the cosmic ledger. Fast forward to modern particle physics, and monopoles take on even greater significance. Grand unified theories, ambitious frameworks aiming to merge electromagnetism with the strong and weak nuclear forces practically demand their existence. These theories suggest that in the extreme energies of the early universe, a phase transition occurred, freezing magnetic monopoles out of the primordial soup like cosmic icicles. Some calculations estimate we should be swimming in them today, with relics drifting through space like silent, magnetically charged ghosts. So where are they? That's where experiments like Mo-Edel come in, literally hunting for needles in the cosmic haystack. Detectors at CERN use layers of special plastic trackers, waiting for the distinctive damage a monopole would leave as it tears through matter. Unlike ordinary particles, a monopole wouldn't just interact electromagnetically. Its isolated magnetic charge would disrupt atoms in a unique, catastrophic way. Think of it like dragging a magnet through a pile of iron filings. The trail left behind would be unmistakable. Other proposals involve superconducting loops that would catch passing monopoles, their persistent currents disrupted by the intruding magnetic charge. Yet despite decades of searching from deep underground labs to high-altitude balloon experiments, not a single monopole has been confirmed. Some theorize inflation diluted their numbers to near zero, while others suggest they're hiding in plain sight, masquerading as heavy, exotic particles we haven't yet recognized. There's even a wild possibility that monopoles could catalyze proton decay, turning ordinary matter into energy in a flash, a process that would make them both destroyers and potential power sources beyond our wildest dreams. Whether they're relics of the universe's fiery birth or figments of our mathematical imagination, magnetic monopoles force us to confront deep questions. Are the symmetries we perceive fundamental, or is nature more anarchic than we dare admit? The hunt continues, driven by the thrilling possibility that discovering even one could rewrite textbooks, proving that sometimes the most elusive ideas are also the most revolutionary. Imagine slicing through the fabric of space-time with an impossibly thin wire, one so fine it has no thickness whatsoever, yet contains more mass than an entire galaxy condensed into a single line. This is the mind-bending reality of cosmic strings, hypothetical wrinkles in reality left over from the universe's explosive infancy. Like cracks forming in ice as water freezes, these one-dimensional defects might have formed when the fundamental forces of nature underwent drastic phase transitions moments after the Big Bang. To visualize how they warp space, picture stretching a piece of cheesecloth tight. Now pinch one thread and pull it upward. The surrounding fabric distorts dramatically, creating a steep funnel around the tension line. Cosmic strings do something similar to space-time itself. Their incredible density, think a billion tons per centimeter, curves space so severely that light bends around them, creating double images of distant galaxies. If one passed through your room right now, you wouldn't feel a thing, but a ruler held sideways might suddenly show two sets of numbers as light takes different paths around the string's gravitational well. What makes these filaments truly extraordinary is how they might reveal themselves. Unlike black holes, cosmic strings don't have endpoints. They either form infinite loops or stretch across the entire universe. When two strings cross, they can reconnect violently, releasing bursts of gravitational waves that ripple through space-time like splashes from a cosmic whipcrack. Advanced detectors like LIGO might soon catch these unique signatures, high-frequency waves with telltale cusps where the string's curvature becomes infinitely sharp. Some theories even suggest such an event could explain fast radio bursts, mysterious, millisecond-long blasts of energy from deep space. Then there's the even stranger cousin of cosmic strings, textures. If strings are linear defects, textures are point-like knots in spacetime's fabric, formed when energy fields get tangled during symmetry-breaking phase transitions. Picture a ball covered in hair that's been combed flat everywhere except one stubborn cowlick that's essentially a texture in quantum fields. These rare defects would be fleeting, collapsing under their own energy and possibly producing intense bursts of gravitational or electromagnetic radiation. If one unraveled near Earth today, it might briefly light up our sky like a supernova before vanishing without a trace. The hunt for these space-time scars isn't just theoretical gymnastics. If discovered, cosmic strings could provide a direct window into unification energy scales we'll never recreate in particle colliders, clues about how gravity married the other forces when the universe was hotter than a trillion suns. Their existence would also support cosmic inflation, as the rapid stretching of space could have amplified quantum fluctuations into macroscopic defects. Some cosmologists speculate that certain anomalous cold spots in the cosmic microwave background might even be shadows where a cosmic string's gravity subtly warped ancient light. What's astonishing is how these relics challenge our notions of what's real. Unlike planets or stars, cosmic strings and textures aren't made of matter, they're pure geometry, kinks in spacetime itself that weigh nothing yet distort everything. They remind us that the universe isn't just filled with objects, but with the dynamic interplay of space, time, and energy, a tapestry where even the wrinkles tell a story. Neutrinos are the universe's ultimate escape artists, particles so ghostly, they can pass through light years of lead without a single interaction. Born in the nuclear furnaces of stars, the hearts of supernova, and even the Big Bang itself, these nearly massless particles flood the cosmos, streaming through you right now by the trillions every second. But their most bewildering trick isn't just slipping through matter untouched, it's their ability to shape-shift mid-flight, morphing between three distinct flavors like a chameleon cycling through colors. This quantum magic, called neutrino oscillation, forced us to rewrite the standard model of particle physics. The discovery began with a solar mystery. For decades, experiments detected only a third of the neutrinos predicted by theories of how the sun burns. The solution: these missing neutrinos weren't gone, they'd simply changed costumes. As electron neutrinos raced from the sun's core, they oscillated into muon and tau neutrinos, invisible to detectors tuned for their original form. Picture mailing a letter that transforms en route from paper to stone to smoke, yet still arrives intact. That's the paradox of neutrinos. Their identity depends on when and where you look. Ice Cube, a telescope buried deep in Antarctic ice, captures these cosmic ghosts in act. When a rare neutrino does collide with an atom, it creates a secondary particle moving faster than light in ice, though slower than light in a vacuum, emitting a blue shockwave called Cherenkov radiation. In 2013, Ice Cube spotted two neutrinos with energies 1,000,000 times greater than those from our Sun, dubbed Bert and Ernie, hailing from beyond our galaxy. These messengers from cataclysms like flaring black holes or colliding neutron stars carry intel no light beam could, traveling undisturbed from the universe's most violent corners. Supernova rely on neutrinos as their hidden demolition crew. When a massive star collapses, 99% of its energy erupts not as light, but as a neutrino pulse so intense, it can outshine all the stars in the observable universe combined for seconds. Computer simulations show how these neutrinos, ricocheting in the collapsing core, create pressure waves that literally blow the star apart. The 1987 supernova in the Large Magellanic Cloud offered proof. Detectors caught a handful of these neutrinos arriving hours before the visible explosion, exactly as models predicted. What makes neutrinos so transformative isn't just their strangeness, but what they reveal about the universe's imbalances. Their tiny but non-zero masses hint at physics beyond the standard model, possibly explaining why matter dominates antimatter in our cosmos. Next-generation detectors like DUNE will study oscillations with unprecedented precision, using liquid argon tanks to catch neutrinos fired through Earth from particle accelerators. Every oscillation they record is a cipher, a clue about how the universe's faintest particles might hold answers to its biggest questions. So the next time you feel nothing passing through you, remember, you're submerged in an ocean of shape-shifting phantoms, each carrying secrets from the birth of stars to the asymmetry of existence itself. Neutrinos don't just defy expectations, they rewrite the rules of reality, one flavor change at a time. Quantum entanglement might be the strangest handshake in the universe, a connection so intimate that altering one particle instantly affects its partner, no matter how far apart they are. Einstein called it spooky action at a distance, and for good reason. Imagine tossing two coins in opposite directions, and no matter how far they travel, they always land on matching sides. Now replace those coins with particles, and you've got entanglement, a bond that defies our classical intuition about how space and time should work. The magic unfolds in experiments like the famous EPR paradox. Take a pair of entangled electrons with opposite spins, measure one as up, and its twin will always be down, even if it's on the other side of the galaxy. There's no signal traveling between them, no hidden wire. It's as if the universe maintains a secret ledger, updating entries faster than the speed of light. Researchers have tested this across staggering distances, like the 2017 Chinese Misha satellite experiment, which beamed entangled photons over 1,200 kilometers apart. The results, the correlation held, proving this quantum link isn't broken by earthly distances. But here's where it bends reality further. Entanglement might not just be a quirk of particles, it could be stitching space-time itself together. The ER equals EPR conjecture, proposed by physicists like Juan Maldacena, suggests that entangled particles are connected by microscopic wormholes, bridges in spacetime's fabric. Picture two holes in a sheet of paper, linked by a tunnel folded through a higher dimension. If true, entanglement isn't just spooky, it's the universe's way of tying itself into knots we're only beginning to untangle. This raises jaw-dropping possibilities. Quantum teleportation exploits entanglement to transmit information, not by sending particles, but by leveraging this invisible bond. In 2022, scientists shattered records by teleporting quantum states over 44 kilometers with near-perfect fidelity. And in labs worldwide, researchers are building quantum networks where entangled photons act as unhackable keys, creating encryption that collapses if eavesdropped. Yet the deepest mystery remains: how does entanglement know to sink faster than light? Some theories suggest particles aren't separate at all, that beneath reality's surface, everything is part of a unified quantum field, with entanglement revealing the seams. Others propose retrocausality, where future measurements influence past states. Whatever the answer, entanglement forces us to confront a truth more bizarre than fiction. The universe isn't just connected. It's speaking in whispers we're only starting to hear. The universe might be hiding its true nature behind the ultimate illusion. What if everything you see, touch, and experience is nothing more than an elaborate cosmic projection? This is the heart of the holographic principle, one of the most radical ideas in modern physics. Picture watching a 3D movie without glasses. the depth feels real, but it's all just light on a flat screen. Now scale that up to cosmic proportions. The theory suggests that our seemingly three-dimensional reality could be encoded on a distant two-dimensional surface, like a hologram where every event inside a volume is perfectly mirrored on its boundary. The concept first gained traction as scientists wrestled with black holes and their infamous information paradox. When matter falls into a black hole, what happens to all the information it contained? Quantum mechanics insists information can't be destroyed, but black holes seem to evaporate over time, leaving no trace. Enter physicist Gerard T. Hooft and later Leonard Susskind, who proposed a solution. What if the information isn't lost? Instead, it's smeared across the black hole's event horizon, imprinted like data on a cosmic hard drive. The three-dimensional objects that fell in, just shadows of their true selves, now existing as data on a 2D surface. This idea crystallized further with the AD/S/CFT correspondence, a mathematical framework where a higher dimensional universe like our own corresponds perfectly to a theory operating on its lower dimensional boundary. Think of it like a sci-fi holodeck where every object inside the room is defined by patterns of light on the walls. In this case, the walls could be the edges of the universe itself, and we're just the projected images. String theorists use this principle to swap impossible-to-solve problems in 3D space for more manageable equations on a 2D surface, like translating a complex sculpture into a detailed blueprint. Visualizing this isn't easy, but imagine peeling an orange and laying the skin flat. Every bump and curve of the 3D fruit is preserved in the 2D peel, just stretched and distorted. Similarly, the holographic principle suggests that the information making up your body, your thoughts, even the stars overhead, might actually live on a flat surface trillions of light years away, with our 3D world just an emergent property. Experiments at Fermilab's holometer have searched for evidence of this pixelation of spacetime, hunting for quantum fuzziness that might betray the universe's true digital nature. So far, no smoking gun, but the implications are staggering. If true, the holographic principle would mean that black holes, quantum gravity, and the very fabric of reality are far stranger than we ever imagined. It challenges the most basic assumptions about space, time, and what it means to exist. The universe isn't just a stage, it might be the projection of something far more fundamental, written on the walls of reality itself. There's a theory about the end of the universe so unsettling, it makes black holes look quaint by comparison. Picture space itself like a frozen lake in winter, seemingly solid, stable, and enduring. But what if beneath that serene surface lurked an abyss of unstable nothingness, waiting for the slightest provocation to shatter everything? This is the nightmare scenario of vacuum decay, where the very fabric of reality could collapse like a house of cards, rewriting the laws of physics in an instant. It all hinges on the Higgs field, the invisible energy ocean that gives particles their mass. Most of us think of it as a static backdrop, but quantum field theory paints a far more precarious picture. The Higgs might exist in a false vacuum, a stable-seeming state that's actually like a marble resting on the edge of a bowl. Given enough time, or the right nudge, it could roll downhill into a lower energy state, triggering a cataclysmic phase transition. Imagine a bubble of true vacuum forming somewhere in space, expanding at the speed of light as its boundary converts everything it touches. Atoms, stars, even space-time itself would reconfigure according to new, unknown rules. The diagrams scientists use to illustrate this are deceptively simple, gentle curves representing energy states, with our universe perched on a precarious plateau. But the implications are anything but mild. A single quantum fluctuation or high-energy experiment, some fear even particle colliders like the LHC, could theoretically nucleate this lethal bubble. Once it begins, there's no stopping it. The transition would propagate outward, erasing chemistry as we know it. Fusion in stars, the bonds in DNA, even the structure of matter. all would unravel in a silent, invisible wave. What makes vacuum decay so chilling isn't just its inevitability, but its unpredictability. The Higgs field could remain metastable for billions of years or collapse tomorrow. Some calculations suggest we're safe, with the universe's current state lasting longer than its projected lifespan. Others argue we're already in the process of decaying, with the bubble's boundary racing toward us from some distant galaxy. There's no way to know until it arrives, no warning, no aftermath, just an instant where the rules of existence change forever. Yet this doomsday scenario holds a strange beauty. If vacuum decay is possible, it hints at a multiverse where other bubbles with different physics exist beyond our cosmic horizon. Our universe might just be one ephemeral configuration in an infinite foam of possibilities, each with its own laws, its own forms of matter. The instability we fear could be the engine of creation elsewhere, birthing realities we can't begin to fathom. For now, vacuum decay remains a spectral what if, a reminder that our cosmic order is more fragile than it appears. But it also underscores something profound: the laws we take as fixed might just be temporary, a fleeting balance in an ocean of potentials. Whether that's terrifying or exhilarating depends on how you look at it. One thing's certain: the next time you gaze at the stars, remember they shine because the void beneath them hasn't decided to rewrite the rules yet. Deep in the cosmic shadows, an almost weightless ghost could be holding galaxies together while solving one of physics' greatest symmetry puzzles. Axions, hypothetical particles so light they make neutrinos seem hefty, were first dreamed up to fix a glitch in quantum chromodynamics. The strong nuclear force which binds quarks inside protons strangely doesn't care if you flip the universe's charge and parity simultaneously. A symmetry called CP that should be violated according to theory, yet isn't observed. This glaring mismatch led physicist Roberto Pexi and Helen Quinn to propose an elegant solution in 1977, a new quantum field that relaxes into balance, producing axions as its ripples. What makes axions doubly fascinating is their potential dual role. These particles, with masses potentially 1 trillion times lighter than electrons, could account for the universe's missing dark matter. Picture a galaxy like our Milky Way, not just surrounded by a halo of invisible particles, but permeated by an ultra-fine quantum fog. Countless axions drifting through every cubic centimeter of space, their collective gravity sculpting cosmic structures. Unlike WIMP that interact weakly, axions would behave more like a bizarre quantum fluid, their wave-like nature spreading across light years. The hunt for these elusive particles resembles listening for a cosmic whisper in a hurricane. The axion dark matter experiment uses superconducting microwave cavities chilled near absolute zero. If axions exist, they should occasionally convert to photons in strong magnetic fields. The team tunes these cavities like radio dials across billions of possible frequencies, each corresponding to different axion masses. It's akin to searching for one specific snowflake in a blizzard, except the snowflake only appears when you sing the exact right note. Recent upgrades using quantum amplifiers have pushed ADMC's sensitivity into uncharted territory. In 2021, they ruled out certain axion mass ranges with unprecedented precision, narrowing the search. Parallel efforts like CAP in South Korea and Haystack in the US employed different techniques, from squeezing quantum noise to exploiting exotic materials. Even astrophysical clues hint at axions. Some scientists speculate these particles might explain anomalous stellar cooling observed in white dwarfs and neutron stars, where heat vanishes faster than standard physics predicts. The implications stretch far beyond dark matter. If discovered, axions could reveal hidden dimensions of reality through their predicted connections to string theory. Certain models suggest axions might cluster into bizarre macroscopic objects, axion stars, with planet-like masses but sizes smaller than an atom, or even form oscillating clouds around black holes detectable by gravitational wave observatories. Some theorists propose that early universe action fields could have seeded primordial black holes or left fingerprints in the cosmic microwave background. What's tantalizing is how axions weave together disparate cosmic puzzles. They offer a bridge between particle physics' tiniest scales and the vast architecture of galaxies, a single solution to two profound mysteries hiding in plain sight. Every null result from experiments like ADAMS isn't just ruling out possibilities, it's sharpening our understanding of where to look next. Whether axions remain hypothetical or emerge as reality's next great revelation, their pursuit exemplifies science at its most ambitious, probing the invisible threads that might stitch the universe together. What if we've been misreading the universe's handwriting? For decades, dark matter's gravitational fingerprints have been the go-to explanation for why galaxies spin faster than visible matter alone can account for. But there's a radical alternative, one that rewrites the rules of gravity itself. Modified Newtonian dynamics, or MUND, proposes that on cosmic scales, gravity doesn't fade as quickly as Newton or Einstein predicted. Instead of invoking invisible matter, this theory suggests we've simply been using the wrong equation all along. The idea took root in the early 1980s when physicist Mordechai Milgrom noticed something peculiar about galactic rotation curves. Stars orbiting a galaxy's edge should slow down, just as Pluto moves more sluggishly than Mercury around the Sun. Yet observations showed outer stars whipping around at nearly the same speed as inner ones, as if gripped by some unseen hand. Milgrom's breakthrough was questioning whether the hand belonged to dark matter or a flaw in our gravity math. His calculations revealed that by tweaking Newton's second law at extremely low accelerations, about 1/10,000,000th of Earth's gravity, those confounding rotation curves snapped into perfect alignment. Visualizing MUND predictions side by side with standard lambda models is like comparing two interpreters decoding the same cosmic message. In lambda universe, rotation curves smooth out because dark matter halos add gravitational oomph where visible matter thins. MUND universe needs no such shadowy scaffolding. Its adjusted equations naturally produce flat rotation curves where Newtonian physics fails. Computer simulations highlight the difference starkly. Galaxies in lambdactum resemble chandeliers, their visible stars dangling from intricate dark matter frameworks, while MUND galaxies glow like self-contained lanterns, their outer stars held fast by gravity's revised rules. But MUND isn't just a galactic one-trick pony. It's scored unexpected wins, like perfectly predicting the velocity dispersion of star clusters where dark matter models fumble. The bullet cluster, often hailed as dark matter's smoking gun because its visible gas and gravity appear divorced, might not be the knockout punch it seems. Some MUND variants incorporate relativistic extensions like TVS tensor vector scalar gravity, which bend spacetime differently than general relativity to explain such anomalies without invisible mass. Yet the theory faces its own cosmic hurdles. Large-scale structures like galaxy clusters still seem to need extra mass, and the cosmic microwave background's fluctuations align neatly with lambdactum predictions. Critics argue MUND adjustments are ad hoc, a cosmic fudge factor no more elegant than inventing dark matter, but proponents fire back. Maybe both theories are half right. Emerging hybrid ideas suggest gravity could behave unusually and exotic particles might exist, weaving a tapestry where neither approach tells the whole story alone. At its heart, MUND forces us to confront an uncomfortable truth. Our understanding of gravity is built on a staggeringly small sample size. We've tested it in solar systems and pulsar binaries, but galaxies and beyond. That's uncharted territory. Whether MUND ultimately revolutionizes physics or serves as a cautionary tale, its value is undeniable. It keeps us questioning the invisible assumptions holding our universe together. After all, history shows that sometimes the most profound discoveries begin with two simple words. What if, for centuries, physicists have mapped reality with just four fundamental forces: gravity, electromagnetism and the strong and weak nuclear forces. But flickering anomalies in atomic experiments hint at something unsettling, a fifth force lurking in the quantum shadows. Picture a conductor leading an orchestra with 4 sections, only to hear mysterious notes no instrument should play. That's the enigma researchers face when certain atomic nuclei decay in ways that defy conventional physics, emitting unexpected energy signatures at precise angles. These peculiar patterns might be cosmic breadcrumbs pointing toward a force unknown. The intrigue crystallized around an anomaly dubbed X17. In 2015, Hungarian physicists spotted bizarre jumps in the energy spectra of beryllium-8 atoms as they decayed. The data showed excess positron-electron pairs parting at exactly 140 degrees, a fingerprint suggesting an unknown particle with a mass of 17 megaelectronvolts was briefly mediating the interaction. When their 2019 follow-up with helium nuclei produced the same angular bump, the scientific community split. Could this be the first evidence of a force carrying boson outside the standard model? Critics argue statistical flukes or experimental artifacts, while proponents point to the uncanny reproducibility across different nuclei. Parallel detective work unfolds in basement labs where torsion balances hunt for hidden forces with exquisite sensitivity. The Earth-Wash Group at the University of Washington suspends donut-shaped pendulums in vacuum chambers, shielding them from all known forces to measure deviations at a Tonton scales equivalent to detecting the weight of a virus. Their experiments test whether gravity's inverse square law holds at micrometer distances, where some theories predict a fifth force might emerge. Intriguingly, certain datasets reveal tiny tugs that vanish when rechecked, like cosmic will-o'-the-wisps. What makes this search revolutionary isn't just the particle hunt, it's the potential to rewrite physics' rulebook. A fifth force could explain dark energy's repulsive push, or why the universe favors matter over antimatter. Some theories link it to protophobic interactions, where the new force ignores protons but couples to neutrons, a bizarre selectivity that would upend our understanding of charge. Others propose forces mediated by hypothetical dark photons that occasionally flicker into our visible universe. The stakes are monumental. Confirming X17 or similar anomalies would crack open the standard model like an egg, revealing physics beyond our wildest conjectures. Until then, these whispers from atomic nuclei and hypersensitive balances keep scientists oscillating between skepticism and excitement, probing the edges of reality for cracks where new forces might be hiding. One thing's certain, if such a force exists, its discovery wouldn't just add a chapter to physics, it would tear up the textbook and start anew. Time crystals sound like something ripped from a sci-fi novel, structures that repeat not in space, but in time, ticking endlessly without energy input like cosmic clocks wound by the universe itself. Unlike any other form of matter, these bizarre creations defy equilibrium, oscillating between states perpetually without ever settling into rest. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, sparking skepticism until lab experiments in 2017 made the impossible tangible. Picture a diamond with atoms not just arranged in a lattice, but one where the entire structure rotates predictably, say, left then right forever, even at absolute zero. No energy goes in, none comes out, yet the rhythm never fades. Creating these temporal oddities requires bending quantum rules. Researchers at the University of Maryland forged the first time crystal by trapping a chain of ytterbium ions in intersecting laser beams. Like a metronome nudged only once but swinging indefinitely, the ions flipped spins in a fixed cycle, their pattern repeating in time rather than space. What's mind-bending is how they sidestep thermodynamics tyranny. Normal systems lose energy to entropy, but time crystals exploit quantum many-body localization, a phenomenon where disorder freezes particles mid-interaction, preserving their dance indefinitely. It's like a wound-up toy that never unwinds because its gears are perpetually jammed in just the right way. The potential applications read like a futurist's wish list. Quantum computers plagued by decoherence could use time crystals as fault-resistant memory. Their stable cycles might encode qubits immune to external noise, solving one of the field's biggest hurdles. Or consider precision sensors, imagine gyroscopes leveraging time crystals' unerring rhythms to navigate spacecraft with unprecedented accuracy. Some theorists even speculate they could model complex systems like financial markets or neural networks, their predictable yet dynamic behavior mirroring real-world chaos better than static equations. Yet the deepest allure lies in fundamental physics. Time crystals challenge our understanding of time symmetry, suggesting new phases of matter beyond solid, liquid, or plasma. They hint at exotic possibilities like time quasi-crystals with non-repeating but ordered patterns, or four-dimensional spacetime crystals oscillating across multiple dimensions. Labs are already racing to engineer larger, more robust versions, probing whether these structures could emerge naturally in neutron stars or other extreme cosmic environments. For now, time crystals remain fragile lab curiosities, their ticks measured in microseconds, but their existence proves something profound, that matter can break time's symmetry just as ordinary crystals break spatial symmetry, opening a portal to physics we've only begun to imagine. The universe, it seems, still holds toys in its toy box stranger than any we've dreamed up. Imagine a substance that defies every intuition about motion. When you push it, it accelerates toward you instead of away. This is the bizarre reality of negative mass, a hypothetical form of matter where the usual rules of inertia flip upside down. If you kicked a ball made of this strange material, it wouldn't sail forward. It would come hurtling back at you like a boomerang with a mind of its own. While it sounds like pure fantasy, negative mass isn't just science fiction. Theoretical models suggest it could exist, and recent lab experiments have even created analogues that behave eerily similar. Einstein's equations of general relativity don't forbid negative mass, they simply demand that such matter would exhibit repulsive gravity. Picture two negative mass objects. Instead of attracting each other like normal matter, they'd repel, accelerating in opposite directions indefinitely. This property has tantalizing implications for futuristic technologies like the Alcubierre warp drive. By surrounding a spacecraft with a shell of negative mass, physicists speculate it might be possible to contract spacetime in front of the ship while expanding it behind, effectively creating a bubble that moves faster than light without violating relativity. The catch: negative mass remains purely hypothetical, and the energy requirements are astronomical. But the math checks out, offering a glimmer of hope for interstellar travel that doesn't rely on brute force propulsion. The real breakthrough, though, comes from the lab. In 2017, physicists at Washington State University engineered a fluid with properties mimicking negative mass. By cooling rubidium atoms to near absolute zero and manipulating them with lasers, they created a state where pushing the fluid caused it to surge backward exactly as negative mass would predict. Think of it like trying to shove a wave toward the shore, only to watch it retreat further into the ocean. These aren't true negative mass particles, but the analogy is uncanny, hinting that nature might have loopholes we haven't yet uncovered. What makes negative mass so revolutionary isn't just its defiance of Newtonian physics, it's the door it opens to reimagining fundamental forces. Could dark energy's cosmic repulsion stem from negative mass fields permeating space? Might neutron stars harbor pockets of this exotic matter in their crushing cores? The questions pile up faster than answers, but one thing's clear. If negative mass exists even in some obscure corner of the universe, it would rewrite our understanding of motion, gravity, and the very fabric of reality. For now, it remains a tantalizing what-if, dangling at the edge of known physics, a reminder that the universe still has surprises up its sleeve. Zoom in far enough on the smooth canvas of space-time, and the picture dissolves into chaos, a seething, turbulent froth where reality itself boils with uncertainty. This is the quantum foam, the universe's hidden texture at scales so small they make atoms look like galaxies. Imagine trying to measure the surface of a calm lake with a microscope powerful enough to see individual water molecules. What seemed serene and solid suddenly erupts into violent churning. At the Planck length, a distance 20 orders of magnitude tinier than an atom, space-time isn't a rigid stage but a frenzied dance of virtual black holes, wormholes, and bubbles flickering in and out of existence. The idea traces back to physicist John Wheeler, who envisioned spacetime's foundation not as a static grid but as an ever-shifting quantum landscape. In this realm, energy fluctuations twist gravity so fiercely that microscopic black holes spontaneously form and evaporate in trillionths of a trillionth of a second. It's as if the vacuum of space is a pot of water at a rolling boil, with bubbles of distorted geometry constantly surfacing and popping. These aren't just mathematical curiosities, they could fracture our intuitive notions of cause and effect. Two events might swap order depending on which quantum foam bubble you're observing, like watching a movie where scenes play out of sequence every time you rewind. Detecting this frenzy isn't about building a better microscope, it's about catching spacetime's tremors in action. Gamma-ray telescopes like the Fermi Space Telescope hunt for subtle distortions in high-energy light traveling across the cosmos. When gamma rays traverse billions of light-years, quantum foam's frothiness should scatter them slightly, like light shimmering through heat waves. In 2019, researchers analyzed Fermi's decade of data, searching for signs that the highest energy photons arrived delayed compared to their lower energy counterparts, a telltale stumble caused by spacetime's graininess. The results were ambiguous but tantalizing, leaving room for future observatories like the Cherenkov telescope array to probe deeper. The implications ripple far beyond academic debate. If spacetime is foamy, it might impose a fundamental limit on precision, a cosmic pixel size, beyond which no measurement can be sharper. Quantum computers could hit unexpected errors from spacetime's inherent fuzziness, while theories of quantum gravity might need to account for this turbulence in their equations. Some models even suggest that traversable wormholes could momentarily crystallize from the foam, offering fleeting shortcuts across the universe before collapsing back into chaos. What's most humbling is how quantum foam forces us to confront the limits of language itself. Words like fabric and foam are crude metaphors for a reality where space and time lose their classical meaning entirely. The closer we look, the more the universe reveals itself as a place of boundless dynamism, a cosmic storm hiding beneath the illusion of stillness. The act of observation might be doing far more than just recording reality. It could be shaping it at the most fundamental level. This startling idea lies at the heart of consciousness collapse theories, where the boundary between observer and observed blurs into something far stranger than we ever imagined. Picture the famous double-slit experiment. When electrons are fired one by one toward a barrier with two openings, they create an interference pattern on the detector screen, as if each particle passes through both slits simultaneously like a wave. But the moment scientists place a measuring device to see which slit each electron actually takes, the interference vanishes. The particles suddenly choose a single path, behaving like discrete objects rather than waves. This quantum enigma suggests that the simple act of looking somehow forces the universe to make up its mind. The von Neumann-Wigner interpretation takes this a step further, proposing that consciousness itself is the trigger that collapses quantum possibilities into concrete reality. In this view, measuring devices alone aren't enough. It takes a conscious observer to finalize the outcome. Think of Schrödinger's infamous cat, neither alive nor dead until someone peers into the box. Wigner even devised a thought experiment where a friend performs the observation first, leaving him to wonder. is the quantum state still unresolved until he hears the result. It's as if reality remains in flux, a sprawling tapestry of maybes until a mind pins it down. Critics argue this veers into solipsism, but supporters point to delayed choice experiments where decisions made after a quantum event seems to retroactively influence its outcome. The implications are dizzying. Our awareness might not just perceive reality but actively participate in its creation. Contrast this with panpsychism, which flips the script entirely. Instead of consciousness collapsing the quantum world, panpsychism suggests consciousness is woven into the fabric of the universe at every level, from electrons to ecosystems. In this framework, particles possess a rudimentary form of experience, and the double-slit experiment's observer effect arises because all matter has an intrinsic inner aspect. Imagine reality as a vast network of tiny perspectives, where even a photon chooses to behave as a wave or particle based on its own minute capacity for interaction. Panpsychists argue this avoids the hard problem of consciousness, how subjective experience emerges from mere atoms, by making it foundational rather than emergent. The debate between these views isn't just academic, it redefines our place in the cosmos. Are we privileged observers, our minds the architects of reality, or participants in a universe already teeming with proto-consciousness, where observation is just another thread in the web? Labs are now testing these ideas with quantum microscopes that track particles without fully collapsing their states, while philosophers wrestle with the hard data. Whether consciousness is the universe's director, its audience, or something far stranger, one thing's clear: the act of looking might be the most powerful force of all. Black holes don't just swallow light, they might be devouring the very fabric of reality itself. This nightmare scenario, known as the black hole information paradox, cuts to the heart of physics' most sacred principle: information can never be destroyed. Think of it like burning a book. The pages turn to ash, but in theory, every word could be reconstructed from the smoke molecules, the heat patterns, even the vibrations in the air. Quantum mechanics insists the universe keeps perfect records, but black holes, they seem to be cosmic shredders, annihilating information beyond recovery. The battle over this paradox has raged for decades, forcing physicists to choose sides between Stephen Hawking's grim calculations and string theory's radical escape hatch. Hawking's bombshell dropped in 1974 when he proved black holes aren't completely black. They emit radiation, now called Hawking radiation, slowly evaporating over eons. Here's the catch: this radiation appears totally random, carrying no trace of what fell in. If you toss an encyclopedia into a black hole, the Hawking radiation coming out would look identical to radiation from a black hole that ate a piano. It's like expecting smoke signals to spell out the book you burned, only to get meaningless static instead. Hawking initially concluded the information was truly gone, violating quantum theory's core tenets. The scientific world reeled. Either our understanding of quantum mechanics was fatally flawed, or black holes were breaching the universe's most ironclad law. String theorists counter with a dazzling alternative: fuzzballs. Imagine a black hole not as a void with a singularity at its core, but as a tangled, vibrating ball of strings, a fuzzball, with no event horizon at all. In this view, information never gets trapped. Instead, it's imprinted on the fuzzball's surface like a hologram, and gradually encoded into Hawking radiation as the black hole evaporates. Picture dunking a sponge in ink. Even as the sponge dries out, traces of the ink remain in its fibers. Similarly, a fuzzball's intricate stringy structure preserves information, releasing it in subtle correlations within the radiation. The debate hinges on one brutal question: what happens at the singularity? Hawking's original math treated spacetime as smooth, leading to infinite curvature where information gets crushed out of existence. But string theory's fuzzballs avoid this cataclysm entirely. Their strings stretch and vibrate, preventing collapse into a point. recent breakthroughs in quantum entanglement add fuel to the fire. The AR=EPR conjecture suggests black holes might be wormholes internally linked by quantum threads, offering hidden pathways for information to escape. Firewall theories, meanwhile, propose a searing wall of energy at the horizon that either scrambles information or burns it up, another twist in the saga. Experimental clues are frustratingly sparse but not absent. Gravitational wave detectors like LIGO listen for echoes in black hole mergers, subtle ripples that might betray a fuzzball structure instead of a classical horizon. Quantum computers simulate toy models of black holes, watching how information scrambles across their event horizons. Each tiny advance inches us closer to knowing whether Hawking's grim prediction or string theory's elegant fix aligns with reality. What's at stake isn't just academic, it's the integrity of physics itself. If information can vanish without a trace, the laws governing reality unravel. But if fuzzballs or some other mechanism preserve it, we're glimpsing a universe far stranger and more interconnected than Einstein ever dreamed. The paradox isn't just about black holes. It's a window into whether the universe forgets or remembers everything. Gravity might not be a fundamental force at all, but an illusion emerging from the universe's relentless drive toward disorder. This audacious idea, known as emergent gravity, flips Newton and Einstein on their heads. Picture a crowded room where every conversation pushes people subtly toward the walls. No single rule dictates their movement, yet the collective effect creates a pattern, an invisible pressure shaping the crowd. Dutch physicist Erik Verlinde proposed that gravity works the same way, arising not from some intrinsic force but from the statistical tendencies of countless microscopic degrees of freedom in spacetime's fabric. At the heart of Verlinde's theory lies entropy, the measure of a system's disorder. In thermodynamics, entropy explains why heat flows from hot to cold or why gas expands to fill a container. Verlinde's radical leap was linking entropy to spacetime itself. Imagine the vacuum not as empty nothingness but as a seething network of entangled quantum bits. When matter disturbs this network, like a stone dropped in a pond, it increases the entropy in that region. The universe, always seeking maximum entropy, responds by redistributing these microscopic degrees of freedom, creating what we perceive as gravitational attraction. It's as if the cosmos is constantly shuffling a deck of cards, and gravity emerges from its relentless shuffling. This is where the analogy to heat gets startlingly precise. Just as heat flows spontaneously from warmer to cooler objects, Verlinde's math suggests gravity is the universe's way of cooling down entropy gradients. A planet warps space not because of some mysterious force, but because its presence creates an entropy imbalance that spacetime rushes to correct. The equations mirror those of thermodynamics, with Newton's gravitational constant popping out naturally from entropy considerations. Even dark matter's effects could be illusions. Verlinde's framework predicts galaxy rotation curves without invoking invisible particles, attributing the anomaly to how entropy responds to cosmic scales. Testing this requires pushing observational technology to its limits. The upcoming LISA mission, a space-based gravitational wave detector, could be the ideal tool. While LIGO catches ripples from stellar mass collisions, LISA million-kilometer arm span will sense low-frequency waves from supermassive black hole mergers. Verlinde's theory predicts subtle deviations in how these waves propagate compared to general relativity's expectations. If spacetime's microstructure truly encodes entropy-driven gravity, merging black holes might leave faint fingerprints in their gravitational echoes, like listening for the difference between a bell ringing in air versus water. Critics argue emergent gravity struggles to explain phenomena like the bullet cluster, where visible matter and gravitational lensing clearly separate. Yet supporters counter that no theory, including dark matter paradigms, explains all observations perfectly yet. What's electrifying is how emergent gravity reframes our cosmic questions. Instead of hunting for dark matter particles, we might be deciphering the universe's thermodynamics. Instead of space-time as a stage, it's a dynamic, holographic system where every galaxy's dance is just the universe tending toward equilibrium. Whether Verlin's vision holds or not, it proves one thing. The deeper we probe gravity's nature, the more it feels like we're reading the universe's hidden thermodynamics textbook. What if dark energy isn't a constant force stretching the cosmos, but something far stranger, particles that actively hide from us? Enter chameleon particles, hypothetical entities so elusive, they change their properties based on surroundings like their namesake reptile. Picture a cosmic game of hide and seek where the seekers are our most advanced detectors, and the hiders are particles that literally slim down their interactions in dense environments. The denser the neighborhood, like Earth's lab-filled realms, the weaker these particles become, slipping through experiments unnoticed, but in the vast emptiness of intergalactic space. They swell in influence, possibly driving the universe's accelerated expansion. This sleight of hand explains why dark energy has been so maddeningly undetectable. Traditional searches assume particles behave uniformly everywhere, but chameleons break the rules. In a planet's gravity well, or even within a vacuum chamber, their mass increases dramatically, stifling their effects to near zero. Only where matter thins out, like the voids between galaxy clusters, do they relax, exerting a repulsive force that could account for dark energy's signature push. It's as if these particles have an innate shyness, retreating from scrutiny where humans might look, yet dominating the cosmic stage where few tools can reach. Breaking their camouflage requires ingenious methods. Atom interferometry, a technique so precise it can measure faint gravitational waves, is now being weaponized in the hunt. Experiments like the one at the University of California, Berkeley, suspend ultra-cold atoms in vacuum chambers, watching for subtle deviations as chameleons nudge them. The trick is isolating regions of varying density to provoke the particles into revealing themselves. Think of it like luring a chameleon out of hiding by carefully shifting the colors of its environment until its camouflage fails. Other approaches, like the Gamvi chameleon experiment, use strong magnetic fields to coax the particles into producing detectable photons, though success remains elusive. The implications, if discovered, would rewrite cosmology. Unlike static dark energy models, chameleon fields could offer dynamic explanations for why cosmic acceleration seems to vary over time. Some theories even link them to quintessence, a fluid like dark energy that evolves with the universe, but the theories get wilder. Certain string theory models suggest chameleons might be higher dimensional particles, leaking into our 3D space, their properties warped by the geometry of hidden dimensions. Others speculate they could mediate a fifth force, one that fades on Earth but shapes galaxies in ways we've mistakenly attributed to dark matter. For now, chameleon particles remain tantalizing maybes. Yet their very elusiveness makes them compelling. In a universe where dark energy constitutes 68% of everything, yet leaves no direct trace, perhaps the answer isn't better detectors, but smarter hiding places. The hunt continues, not just for the particles themselves, but for the unsettling possibility that the cosmos is far more adaptive, far more aware of being watched than we ever dared imagine. Imagine the emptiest place you can think of, a void so vast it could swallow thousands of galaxies without a trace. Now picture this cosmic nothingness crackling with invisible magnetic fields, their tendrils stretching millions of light years across the abyss. These aren't your typical stellar or galactic magnetic fields, the kind that twist around stars or spiral through galactic arms. These are primordial relics, perhaps dating back to the universe's first trillionth of a second, lurking in regions so sparse they make Earth's interplanetary space look crowded. Scientists first stumbled upon these ghostly fields by tracking cosmic rays, high-energy particles from deep space that zigzag across the universe. When researchers mapped their paths, they noticed something bizarre. Even in the bleakest voids between galaxy clusters, these particles weren't traveling in straight lines. Something was bending their trajectories, and the only explanation was a pervasive magnetic field threading through the emptiness. The discovery was like realizing the air in a vacuum chamber still carries the faintest hum of electricity. Theories about their origin split into two cosmic camps. One suggests these fields are survivors from the Big Bang's aftermath, when the universe was a seething plasma of charged particles. As spacetime expanded, these fields stretched and froze into the voids, preserved like fossils in cosmic amber. Another camp argues they were forged later by the universe's first generation of stars and galaxies, their outflows of charged particles seeding magnetic turbulence that bled into intergalactic space. Simulations show both scenarios could work, but the smoking gun would be detecting the field's unique fingerprint in the cosmic microwave background. Subtle swirls imprinted when these ancient magnets interacted with light just 400,000 years after the Big Bang. What's truly wild is how these fields shape the universe's most energetic phenomena. Cosmic rays, protons, and atomic nuclei accelerated to near light speed ride these magnetic highways like surfers on an invisible wave. Without these fields, ultra-high-energy cosmic rays would blast through the void unimpeded, arriving at Earth with clues about their distant origins intact. Instead, their paths twist into cryptographic puzzles, forcing scientists to play detective with particles that may have traveled for billions of years before reaching us. Some researchers speculate these fields could even funnel dark matter, subtly guiding its distribution through the cosmos. The hunt to map these ghostly fields is pushing technology to its limits. Radio telescopes like the low-frequency array scan the sky for synchrotron radiation, the faint glow emitted when electrons spiral along magnetic field lines. Others analyze how these fields polarize light from distant quasars, turning the entire universe into a giant Faraday rotator. Each new observation peels back another layer of the mystery, revealing a cosmos far more magnetically alive than we ever imagined. What's humbling is realizing that even the universe's emptiest corners aren't truly empty. They're threaded with whispers from creation's first moments, a hidden architecture shaping everything from rogue particles to the fate of galaxies. The next time you gaze at a seemingly blank patch of night sky, remember, there's no such thing as nothingness in this universe, only forces we're just beginning to see. Neutron stars are nature's ultimate pressure cookers, cosmic corpses so dense, a single teaspoon of their material would weigh 1 billion tons on Earth. But beneath their crushing gravity lies a quantum wonderland stranger than fiction. Deep in their cores, protons and electrons get squeezed together until they surrender, merging into a surreal sea of neutrons that flow without friction, a phenomenon called neutron superfluidity. Picture an Olympic swimming pool filled with honey, but instead of sluggish resistance, the honey moves like it's been electrified, every molecule perfectly synchronized in a frictionless dance. That's the bizarre reality inside a neutron star, where quantum mechanics trumps even the most extreme conditions. These stars occasionally reveal their inner chaos through glitches, sudden, inexplicable speed-ups in their rotation. Imagine a figure skater pulling their arms in mid-spin, but in this case, no visible motion explains the change. Astronomers trace these jumps to superfluid vortices inside the star, suddenly unlocking and transferring angular momentum outward. It's as if the star's crust gets yanked forward by an invisible whip cracking beneath the surface. The 2019 glitch of the Vela pulsar remains one of the most dramatic examples. The star suddenly spun 2% faster in an instant, a seismic shift for an object with the sun's mass crammed into a city-sized sphere. NASA's NICER telescope is peeling back the neutron star's layers like a cosmic onion. Mounted on the ISS, this X-ray observatory maps hotspots on neutron star surfaces with precision, inferring the physics below by tracking how light bends and flickers across terrain warped by gravity 100 billion times stronger than Earth. Nicer data revealed that some neutron stars have mountains deformations less than a millimeter tall, yet massive enough to ripple space-time and emit gravitational waves. These subtle bumps might be frozen in place by quantum quirks in the superfluid below, like wrinkles in a rug anchored by invisible furniture. The implications stretch far beyond stellar curiosities. Neutron star superfluids might be our best laboratory for studying quantum chromodynamics at densities impossible to replicate on Earth. Some theories suggest their cores host even weirder phases, poster nuclei arranged in sheets and tubes, or free-floating quarks unchained from protons. Others speculate that colliding neutron stars could eject droplets of this primordial soup, creating exotic nuclei not seen since the Big Bang's first seconds. Yet the biggest mystery remains how superfluidity shapes the star's magnetic field, which can be 1 trillion times stronger than Earth's. The interplay between superconducting protons and superfluid neutrons might twist these fields into knotted configurations, powering the star's lethal gamma-ray jets. Every glitch, every X-ray pulse is a cipher, a clue about quantum physics pushed to its limits. The next time you see a pulsar's steady blink, remember, it's not just a dead star's heartbeat. It's the echo of a quantum storm raging inside. If black holes are cosmic vacuum cleaners, then white holes are their theoretical opposites, cosmic fire hydrants spraying matter and energy outward instead of sucking them in. These hypothetical objects emerge when you hit the rewind button on Einstein's equations, creating a region of spacetime where nothing can enter, only escape. Picture a black hole's event horizon turned inside out. Instead of a point of no return, it's a point of no admission. But here's where it gets stranger. Unlike wormholes, which bridge 2 points in space, white holes aren't traversable portals. They're more like cosmic ejector seats, violently expelling everything that ever fell into their black hole counterpart. Loop quantum gravity, a framework aiming to unify general relativity with quantum mechanics, gives white holes surprising credibility. The theory suggests that when a black hole's collapse reaches the Planck scale, quantum effects could rebound the singularity into a white hole. It's like squeezing a spring to its limit. The compression reaches a breaking point and the energy recoils. Calculations show this transformation could happen over unimaginable timescales, meaning primordial black holes formed in the early universe might now be erupting as white holes, their fireworks slowed to a crawl by relativistic time dilation. Some speculate that fast radio bursts, those mysterious milliseconds-long blasts of cosmic radio waves, could be white holes coughing up quantum information after eons of silence. Penrose diagrams, those mind-bending maps of spacetime, reveal even wilder possibilities. When you chart a black hole's lifespan, its future singularity curves toward infinity. But if you extend the diagram beyond classical physics, the singularity can bounce, morphing into a white hole's past singularity. This creates a theoretical object called an Einstein-Rosen bridge, a black hole eternally connected to a white hole, though any traveler would be ripped apart by tidal forces long before crossing. Modern revisions, like the Hayward metric, propose non-singular black holes that smoothly transition into white holes, offering potential escape routes from what was once considered a one-way trip to oblivion. The catch: white holes violate the second law of thermodynamics by decreasing entropy, making them statistically improbable. Yet quantum mechanics loves a good loophole. If information must escape black holes, as Hawking eventually conceded, then white holes offer a neat solution. They're the universe's recycling plants, converting compressed spacetime back into radiated energy. Whether they're mathematical curiosities or cosmic realities waiting to be discovered, white holes force us to confront a profound truth. In the quantum gravity arena, even the most intuitive cosmic rules might be negotiable. There's a mathematical phantom lurking in particle physics, a substance so strange, it refuses to play by the universe's usual rules of scale. Meet unparticles, hypothetical matter predicted by certain beyond the standard model theories, where particles don't have definite mass or size but instead behave as if they're trapped between dimensions. Picture trying to weigh smoke. The harder you press, the more it slips through your fingers, never settling into a fixed quantity. Unparticles embody this elusiveness, operating under scale invariance, meaning their properties look identical whether you zoom in or out, like a fractal pattern that repeats infinitely at every magnification. The idea emerged in 2007 when physicist Howard Georgi proposed that hidden sectors of reality, fields and particles completely disconnected from our familiar quarks and electrons, might interact with our world through these ghostly intermediaries. Unlike protons or neutrinos with well-defined masses, unparticles would manifest as a continuous spectrum of energy, more like a fluid than discrete bits. Imagine shaking hands with a shadow and feeling not a solid grip, but a strange pressure that somehow fills your palm without any tangible form. This eerie quality could explain anomalies in high-energy cosmic rays, those mysterious particles from deep space that hit Earth's atmosphere with energies far beyond what our accelerators can produce. Cosmic ray observatories like the Pierre-Auger array have detected particles with energies exceeding 10 million times that of the Large Hadron Collider's beams. These ultra-high-energy cosmic rays should interact strongly with the cosmic microwave background as they travel, losing energy over long distances, a phenomenon called the Greisen-Zatsepin-Kuzmin-Gizike cutoff. But some seem to arrive too fresh, as if something shielded them en route. Unparticles could be the cosmic sneaky couriers. Their scale-invariant nature might allow them to mediate energy transfers in ways that evade the Gizike limit, like a stealth plane slipping past radar by scattering signals unpredictably. The hunt for unparticles involves sifting through noise for statistical ghosts. Collider experiments search for missing energy signatures, gaps in momentum where energy vanishes into unparticle interactions. Other approaches track celestial events like neutron star mergers, where unparticle-mediated processes might subtly alter neutrino emissions or gravitational wave patterns. Even black hole physics gets twisted. Unparticles could modify Hawking radiation spectrum, leaving faint thermal fingerprints detectable by next-gen telescopes. What's tantalizing is how unparticles blur the line between particle physics and condensed matter. In materials like graphene, electrons behave as if they're massless, their energy and momentum linked linearly, a hallmark of scale invariance. This parallel suggests unparticles might not just be exotic cosmic flukes but shadows of a deeper symmetry woven into reality's fabric. Whether they're out there or not, their theoretical existence forces us to confront a humbling possibility. The universe's building blocks might not always look like blocks at all, but something far more fluid and strange. Phantom energy isn't just another form of dark energy, it's its apocalyptic cousin. A force so voracious it could literally shred the universe to subatomic confetti. Imagine dark energy's accelerated expansion turned up to 11, where the repulsive force doesn't just push galaxies apart but grows stronger over time, eventually overpowering every binding force in existence. This is the nightmare scenario cosmologists call the Big Rip, and its timeline reads like a horror story written by the laws of physics themselves. The countdown starts subtly. Billions of years from now, phantom energy's grip would first yank galaxy clusters apart, sending neighboring galaxies like Andromeda fleeing faster than light's reach. Next, individual galaxies unravel, stars stripped from their orbits, drifting into the void like dandelion seeds in a hurricane. But the real terror begins when the force turns inward. Planetary systems fracture, then planets themselves. The Earth, if it still exists, will be peeled apart layer by layer, its crust separating from the mantle in slow motion. Even atoms, the universe's last holdouts, wouldn't be safe. In the final microseconds, phantom energy's exponential surge would overcome the strong nuclear force, ripping protons and neutrons into quark soup before spacetime itself frays at the seams. Visualizing this demands confronting timescales that dwarf human intuition. Astrophysicists model the Big Rip's progression using fluid equations where phantom energies, equation of state, parameter, dips below -1, a threshold where its density increases as space expands. Simulations show cosmic structures dissolving like sugar cubes in boiling water. The Milky Way's spiral arms stretch into ghostly streamers, superclusters fracture into isolated islands of stars. Unlike the heat death of the universe, which plays out over near infinite time, the Big Rip has a finite expiration date. Some estimates pin it at around 22 billion years from now, a blink in cosmic terms, though the uncertainties are vast. The implications rewrite cosmic archaeology. If phantom energy dominates, future civilizations or their remnants might detect its fingerprints in the universe's expansion rate. Subtle deviations in supernova brightness or baryon acoustic oscillations could reveal whether dark energy is constant or evolving toward this cataclysmic endgame. Telescopes like ESA's Euclid mission are already mapping these clues, searching for phantom energy's telltale pressure fluctuations across billions of light years. Yet phantom energy's most unsettling quality isn't its destructive potential, it's how it warps our understanding of vacuum energy. In quantum field theory, the vacuum isn't empty but simmering with particle-antiparticle pairs. Phantom energy suggests this quantum foam might have a runaway feedback loop, where expansion begets more repulsion in a self-destructive cycle. It's as if the universe contains its own doomsday switch waiting to be flipped. Whether this scenario is inevitable or merely one possible future hinges on questions we're only beginning to ask. For now, phantom energy remains a specter haunting cosmology's equations, a reminder that the universe's fate might be far more violent and far more strange than we ever imagined. Black holes and neutron stars may dominate the cosmic spotlight, but there's a subtler twist to gravity lurking right under our feet, literally. When massive objects spin, they don't just warp space-time, they twist it, dragging the very fabric of reality around like syrup swirling around a spoon. This phenomenon, called gravitomagnetism, reveals a hidden kinship between gravity and electromagnetism. Just as moving electric charges create magnetic fields, moving masses generate gravitational counterparts that tug on anything nearby. Einstein's equations predicted this effect, formerly known as frame dragging, over a century ago, but detecting it required technology precise enough to measure distortions smaller than the width of a human hair across Earth's entire orbit. Enter Gravity Probe B, NASA's audacious experiment launched in 2004. The spacecraft carried gyroscopes polished to near-perfect spheres, spinning in a vacuum colder than interstellar space. Over 17 months, it measured how Earth's rotation subtly twisted the orientation of these gyroscope spin axes. The results, a deflection of just 37 milliarcseconds per year, like watching a clock's hour hand move 1 degree every 10 million years. Yet this minuscule drift confirmed frame dragging with staggering precision, proving spacetime isn't just a static stage but a dynamic fluid stirred by every rotating mass. The math behind this gets wild. The lens-thirring effect, named after the physicists who derived it in 1918, describes how a spinning planet creates a gravitational vortex. Picture Earth submerged in honey. As it rotates, it pulls the sticky medium around with it. Now replace honey with spacetime itself, and you've got frame dragging. Near a rapidly spinning black hole, the effect becomes extreme. Orbiting particles get whipped around like leaves caught in a drain's whirlpool, their paths spiraling uncontrollably along the black hole's rotational axis. This isn't just theoretical. X-ray observations of accretion disks around black holes show matter orbiting at different speeds depending on its alignment with the spin, a smoking gun for gravitomagnetic chaos. But the implications stretch beyond celestial mechanics. Frame dragging subtly influences satellite orbits, including GPS systems that underpin modern navigation. Ignoring it would introduce errors accumulating to kilometers over time. Future missions like LISA, the space-based gravitational wave detector, will leverage gravitomagnetism to map spacetime's twisted geometry around merging supermassive black holes. Even Earth's weather might feel its touch. Some climatologists speculate polar vortices could couple with frame-dragging effects on atmospheric currents, though the link remains speculative. What's mesmerizing is how gravitomagnetism blurs the line between force and geometry. It's not that spacetime has a structure, it is the structure bending, twisting, and vibrating in response to every rotation in the cosmos. From the slow drag of planets to the violent spins of quasars, the universe is a symphony of swirling spacetime, with Gravity Probe B's gyroscopes as our first tiny tuning forks, finally letting us hear the notes. What if everything you know, every star, every atom, every fleeting thought, is just an elaborate line of code running on some unfathomable supercomputer? This unsettling idea, known as the simulation hypothesis, suggests our universe might not be the base reality but an artificial construct, a cosmic virtual reality so advanced its inhabitants us can't tell the difference. Philosopher Nick Bostrom formalized this modern-day brain twister into a logical trilemma. Either nearly all civilizations go extinct before reaching posthuman status, virtually none choose to run ancestor simulations, or we're almost certainly living in one. The argument hinges on probability. If future civilizations could and would create countless simulated worlds, the math suggests real beings like us are statistically outnumbered by digital ones. But this isn't just philosophy masquerading as science. Physicists have proposed tangible ways to test the simulation idea by hunting for glitches in reality's rendering. One approach looks for pixelation at the Planck scale, the universe's hypothetical smallest unit. Just as a video game has resolution limits where curves reveal jagged edges upon zooming in, spacetime might exhibit similar pixel-like artifacts at scales of 10 to the minus 35 meters. Gamma-ray telescopes like the Fermi Space Telescope have scoured high-energy cosmic rays for signs of this pixelation. If the universe is a lattice-based simulation, ultra-high-energy particles should hit a computational frame rate limit, altering their wavelengths in detectable ways. So far, no smoking gun, but the search continues. Another angle probes quantum mechanics quirks, the observer effect, where particles seem to choose states only when measured, mirrors how video games optimize processing power by rendering only what players observe. The double-slit experiment's wave function collapse could be the universe's version of lazy loading, where unobserved possibilities remain uncomputed to save resources. Even quantum entanglement's spooky action at a distance fits. Correlated particles might simply be linked variables in a cosmic codebase, updating instantly because they're fundamentally the same data pointer. Yet contradictions abound. Simulating every particle in a universe would demand unfathomable energy unless the simulation uses clever shortcuts, like approximating distant stars as low-resolution textures. Some theorists argue that the holographic principle, where a 3D universe's information is encoded on a 2D boundary, is exactly such a shortcut, a cosmic compression algorithm. Others note that mathematical constants like the fine structure constant appear finely tuned for life, hinting at deliberate settings rather than random emergence. The debate splits scientists. Some, like Neil deGrasse Tyson, assign startlingly high odds to us being Sims. Others, like physicist Frank Wilczek, counter that nature's inefficiencies like chaotic turbulence defy the elegance you'd expect from engineered code. Then there's the cosmic irony. If we ever prove we're in a simulation, our creators might just hit delete. Whether reality is rendered or fundamental, the hypothesis forces a humbling perspective. It reframes the search for unified physics as reverse engineering a universe-sized program, and questions whether consciousness itself might be the only real thing in an otherwise synthetic cosmos. So the next time your Wi-Fi glitches or déjà vu strikes, ask yourself, was that a bug or a feature? Our galaxy isn't drifting through space aimlessly, it's being pulled towards something colossal, something hidden behind a cosmic curtain we can barely peer through. Astronomers call this enigmatic force the Great Attractor, a gravitational anomaly so powerful it's dragging the entire Milky Way and thousands of neighboring galaxies toward it at over 600 kilometers per second. The strangest part, we can't see what's doing the pulling. This cosmic tug-of-war was first uncovered in the 1970s when astronomers mapped the peculiar velocities of galaxies, their motions after accounting for the universe's expansion. The Milky Way, Andromeda, and all nearby galaxies were found to be streaming toward a single point in the constellation Centaurus. At first, researchers assumed it was just a massive galaxy cluster, but infrared surveys like 2MASS revealed something far grander. The Great Attractor isn't a single object, it's a gravitational focal point for an unfathomable concentration of mass, equivalent to tens of thousands of Milky Ways crammed into a region of space just a few 100 million light-years across. Peering into this mystery comes with a unique obstacle, the zone of avoidance. This isn't some sci-fi force field, it's the thick band of dust, gas, and stars in our own galaxy's plane that blocks our view of what lies beyond. Imagine trying to study a distant city through a fogged-up window while standing in a neon-lit room. That's the challenge astronomers face when observing the Great Attractor's region. Traditional telescopes relying on visible light are practically blind here. That's where infrared and radio astronomy come to the rescue. Projects like the 2-micron all-sky survey 2MASS pierce through the dust, revealing previously hidden galaxies lurking in the attractor's grip. The images show a sprawling tapestry of galaxies converging like rivers flowing into a waterfall. Even more revealing were X-ray observations, which detected vast clouds of hot gas, telltale signs of immense galaxy clusters hidden behind the Milky Way's glare. One of these, the Norma cluster, sits near the Great Attractor's core, but it's still not massive enough to explain the full pull. The plot thickens when you consider what lies even farther beyond. The Great Attractor itself seems to be moving, caught in the gravitational current of something larger, the Shapley supercluster, a gargantuan structure containing over 20 massive galaxy clusters. This cosmic hierarchy suggests we're witnessing a Russian nesting doll of gravity, where each attractor leads to another, grander one. It's as if the universe is a vast network of hidden watersheds, with galaxies flowing like water toward the deepest valleys of spacetime. What's truly humbling is how much remains uncharted. The Great Attractor is a reminder that even in an age of space telescopes and supercomputers, we're still mapping the shadows of our own cosmic backyard. Every new survey peels back another layer, revealing just how much we've yet to discover about the forces sculpting our corner of the universe. So the next time you look up at the night sky, remember, we're not just observers. We're passengers on a galactic voyage, hurtling toward a destination we're only beginning to understand. The cosmic microwave background should be the ultimate equalizer, a perfectly uniform whisper of radiation left over from the Big Bang, carrying no trace of our insignificant corner of the universe. Yet when scientists peeled back its layers, they uncovered something that defies explanation: eerie alignments between the CMB's largest temperature fluctuations and the plane of our solar system. This bizarre cosmic coincidence, nicknamed the axis of evil, threatens to upend our most basic assumptions about universal isotropy, the idea that the cosmos has no preferred direction. It started with the Wilkinson Microwave Anisotropy Probe WMAP. When researchers mapped the CMB's temperature variations, they expected a random scatter, like static on an untuned television. Instead, the largest hot and cold spots formed a pattern eerily aligned with the ecliptic, the plane where Earth and the planets orbit the Sun. The odds of this happening by chance: less than 1 in 1,000. Later, Planck satellite data confirmed the anomaly, showing that the CMB's quadrupole and octupole moments, its most significant large-scale fluctuations, point suspiciously close to the solar system's orientation. It's as if the universe left a cryptic arrow pointing directly at us, violating the Copernican principle that we don't occupy a special place in the cosmos. Theories attempting to explain this range from the unsettling to the unsettlingly mundane. Some propose it's evidence of primordial structure, relics from a universe that existed before the Big Bang, imprinting patterns on our newborn cosmos like shadows on a cave wall. Others suggest it could be a sign of cosmic topology, where space-time wraps around itself in ways that create preferred directions. But the most provocative idea, that we're seeing contamination from an entirely separate universe brushing against ours in a higher dimensional bulk, leaving gravitational fingerprints in the CMB. Skeptics counter with observational artifacts, dust in our solar system's own backyard. The Kuiper belt and zodiacal cloud could be scattering microwave photons in ways that mimic large-scale anomalies. Others point to the Doppler effect from our galaxy's motion, arguing we're misinterpreting the data. Yet even after correcting for these factors, the alignment persists like a stubborn stain on cosmology's cleanest dataset. The implications are dizzying. If the axis of evil is real, it suggests the universe might have a fundamental orientation, a cosmic North Star that shouldn't exist in standard inflationary models. Future CMB experiments like CMB S4 aim to hunt for polarization patterns that could confirm or debunk the anomaly, while theorists explore models where inflation wasn't perfectly uniform, leaving behind wrinkles that privilege certain directions. One thing's certain, whether it's a window into the pre-Big Bang or just a trick of the light, the axis of evil forces us to confront an uncomfortable truth. The universe might not be as random as we thought, and the deeper we look, the more it seems to be staring right back at us. From the ghostly pull of dark matter to the quantum foam churning beneath spacetime's surface, we've navigated a universe stranger than fiction, one where emptiness crackles with energy, black holes might hide universes, and reality itself could be an illusion. Yet for every mystery we've unraveled, a dozen more lurk in the shadows, defying our best theories. Dark energy's relentless push, the phantom whispers of axions, the cosmic conspiracy of the axis of evil, each one taunting us with questions we can't yet answer. What's breathtaking isn't just how much we've discovered, but how much we haven't. The forces shaping our cosmos are like invisible hands, their fingerprints everywhere, yet their nature just beyond our grasp. Think about that. 85% of the universe's matter is dark matter. 68% of its energy is dark energy, and we have no idea what either of them actually are. Even gravity, the force we thought we understood, might be an emergent illusion, a cosmic sleight of hand hiding deeper truths. And that's the beauty of it. The universe isn't a puzzle with missing pieces, it's an endless labyrinth, each corner revealing new wonders. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Maybe it's lurking in the spin of a neutron star's superfluid core. Maybe it's encoded in the holographic hum of a black hole's event horizon. Or maybe it's something we haven't even thought to question yet. So tell me, which cosmic mystery captivates you? The haunting enigma of white holes, the quantum riddles of entanglement? Drop your favorites in the comments, because the greatest lesson of all is this: the universe isn't just stranger than we imagine. It's stranger than we can imagine, and the adventure to uncover its secrets, that's just beginning.